We are discussing multidimensional unconstrained optimization. We have seen the theory as well as examples of such problems. We have also discussed the significance of gradient in such optimization. Now in this lecture, we will get into a very important family of methods, that is the gradient descent methods. And here we will actually use the gradient information in minimization of multidimensional function. In this lecture, we will look at the theory of one of this gradient descent method, that is known as steepest descent method. We will also solve one problem, at least the part of the problem, using steepest descent method. Gradient descent method is a family of methods. This is not one method. The commonality here is that all such methods, they use gradient information for optimization. In optimization problem, we are trying to find this vector x, which will minimize this function f of x, and this vector we name that as x star. We start from an initial guess x naught, and then we iteratively update this x as k plus 1th iteration is equal to x at kth iteration plus hk dk. Here dk is a vector, that is the descent or search direction. Hk is a scalar, that is the step size. Hk is always positive. When we perform this search, we want to make sure that in every iteration that f x k plus 1 will be less than f x k. In that way, in every iteration the value of this function will reduce, and we hope that eventually we will hit the minimum. So first task is to select a good quality descent direction, and to select this good quality descent direction, we expand this f x k plus 1 in Taylor series, and in this case the independent variable x is a vector, so this is a multivariable Taylor series. So fxk plus 1 is equal to fxk plus hk dk and delta f, their inner product, plus higher order term of the order of hk square. We will neglect all these higher order terms and we will focus on these first two terms only. In that way, we can say that as I go from k to k plus 1th iteration, the change in fx will be this much, that is the delta f is equal to hk, and this is the inner product of dk del fk. You can also call this as the directional derivative, because this is the gradient and this is the inner product of gradient with dk. So this is the directional derivative in the direction of d. So now, because we want this fxk plus 1 will be less than fxk, that means that this del f must be less than 0. Now how do we ensure that? To ensure that, we have to make sure that this dk and this delta f, that is the gradient of f, their inner product should be less than 0. So this is the fundamental theory of gradient descent. How we select this d and h, that will lead to different methods, but any value of d that will obey this relation, that its inner product with this nabla f is less than 0, that is a good descent direction. And this d and this nabla f, their inner product, that is something we call directional derivative in the direction of this dk. Now recall what we were discussing before, that we have these three curves f, g and p. They are essentially same equation with different constants in the right hand side. So here these three curves are plotted, and we have discussed that at this particular blue point, which is -1, 1, if we draw the normal on this red curve, the same line will also be the normal on other curves, that is the gradient direction. And this gradient direction on this particular point is this minus 1, 1 transpose. And we have also discussed that if we follow this gradient direction, then the value of this x square plus 2y square minus 2xy minus 2x will increase at fastest rate. And similarly, if we go against the gradient direction, the value of the same function will decrease at fastest rate. Now, this is the information we will keep in mind for subsequent discussion. So now we come back to this fxy, x square plus 2y square minus 2xy minus 2x. We are talking about this function for quite some time now. And we have seen in our last lecture that this is the contour plot of this function. This is actually a three-dimensional surface. But if we cut the surface parallel to xy plane, we'll see this contour plot. Now, this del f, that is the nabla f, we know that this will be 2x minus 2y minus 2, 4y minus 2x. This gives our gradient direction. So if I take at kth iteration, I have this negative 1, 1 transpose. I am here. At that particular point, my f negative 1, 1, if I plug it in here, it gives me the value of 7. And at this point, if I plug this negative 1, 1, I get this nabla f xk is 6 minus 1, 1 transpose. That means this is the direction of gradient, this blue line. It goes negative in x and then positive in y at 45 degree here. So roughly this is the direction of our gradient. So therefore, for this descent direction dk, I need this dk nabla f, inner product of that, less than 0. So I need a vector which, if I take the inner product with this, will be negative. So let us just say that because this is two-dimensional plane, my dk has these two elements d1 and d2. I can see here this my del f is 6 negative 1 1. So if I take this inner product, it will give me 6 and this minus 1 into d1, 1 into d2. So it will be d2 minus d1. This is my inner product. This is just a scalar quantity. For this product to be less than 0, we need this d2 to be less than d1. As soon as I set d2 minus d1, it will be less than 0. And all this for every d2 minus d1, for every such d1, d2 combination, I can have a feasible descent direction. So which one I'll take? I can have infinitely many descent direction. Which one I can take? And there are various logics on selecting one over other. So let us see some of them. Here we will discuss about steepest descent, and steepest descent tells us that you take that direction in which you can reduce the function at fastest rate. So for instance, this dk nabla f, this inner product, I can write that this is norm of this vector dk, norm of this vector nabla f multiplied by cos theta, that is the theta is the angle between these two vectors dk and gradient. So because this is less than 0, cos theta should be less than 0 because these are the norms which are positive. So cos theta should be less than 0. Minimum of cos theta can be negative 1, and that can happen when theta goes to pi. Therefore, it says that in steepest descent, the angle will select that is pi. So that this could be, we can go as much as possible in shortest distance, as much as possible we want to reduce the function. Since dk and this nabla f, the angle between them is pi, we can say that dk is equal to negative of lambda f xk. So one is going against other. You forget about the magnitude. If one goes against other, that is sufficient. The magnitude part we can take care in step size. But here we are concluding that the descent direction, if it goes against the gradient, that is the steepest direction, or in that direction, the function will decrease at the fastest rate. So we can see the rate of minimization is highest in this direction, and by rate of minimization, we refer to the reduction in the value of the function f over unit distance. If I go unit distance in any other direction, the reduction I'll not get as much as I'll get if I go in this direction, that is against the gradient. Now, of course, we are left with that how do I find hk? And for hk, we have to follow a method of line search. There are many options for getting hk, and all this method, this school of methods, is known as line search method. So let us see what is usually used in steepest descent. Now when we are going to x plus k1, we have already xk is known, dk we have just calculated, because dk we have decided that we will go against the gradient, so we have just calculated dk. So xk and dk are known. Therefore, fx plus k1 is fxk plus hk dk. This is only a function of hk because xk and dk are known. So fxk plus 1 is only a function of hk, and I write that as this phi of hk. So we define the value of hk, that is h, which will minimize this function phi h, that is our hk, which means that I'll go in this direction, I'll go that much as long as this f is being minimized. So how do I then minimize this phi h? Okay, you can see that this is a function of only one independent variable. Minimization of this function will require one-dimensional optimization techniques. Some of those techniques we have already defined, and now you see that those techniques are really useful in multidimensional optimization. Sometimes finding this minimum of this phi at every iteration becomes very expensive. So we try to use some other methods, and other methods means that we just make sure that it is not minimized, but it is at least partially minimized. So as soon as we see that, yeah, my fxk plus 1 is somewhat less than fxk, we go to the next iteration. We use that procedure sometime, and I'll show you how to use that procedure later on. Now we come back to our example of fxy, x square plus 2y square minus 2xy minus 2x. And we have this initial guess of minus 1, 1. I am treating this x vector as x and y, two elements. And we know that xk plus 1 is equal to xk plus hk dk. This is our initial guess, minus 1, 1. And now we have to go to our next, that is, this is 0th iteration. I have to go to first iteration. I'll take this d, that is my descent direction, that is negative of gradient at x0. So d0 will come as minus 6 minus 1, 1. We have already found that the gradient will be 6 minus 1, 1. So here my descent direction is just opposite to that, minus 6 minus 1, 1. So now we have this phi of h, that is fxk plus 1. This is only a function of h, because fxk plus 1, here fx1 is x naught plus h d naught. X naught is known, minus 1, 1. D naught is known, minus 6 minus 1, 1. Therefore x naught plus h d naught, x naught is minus 1, 1, and then this h d naught is this. So if I sum it up, I get 1 minus 6h minus 1, 1. So I put this value over here, and I bring this, so my x is minus 1 plus 6h, y is 1 minus 6h. I put this x and y values here, and based on that, I get the expression of this f x naught plus h d naught, and that is my phi h. You can see that this is a function of h only. So now I have to find the minimum of this function, and for that I'll take the derivative of this function phi h, which gives me minus 60, 1 minus 6h minus 12, and we'll make this 0. H will be h naught when phi prime is 0, and that gives us h naught is 0.2. So I plug this in 0 and I get the value of h, that is 0.2. So now I have my next point then. My x1 will be x naught plus h naught d naught. H naught is this, d naught I have already calculated. I plug everything in, I get 0.2 minus 0.2, that point. So my 0.2 minus 0.2 will be somewhere here. You understand, looking at this figure, that the minimum will be somewhere probably here. And in one iteration, I have jumped from this blue point to this green point. So I came pretty close to this minimum point. Just to look at the value, at this blue point, the value of the function was 7. And now at this green point, this 0.2 minus 0.2, if I plug in this 0.2 and minus 0.2 in this expression, I get that the value of the function at x1 is negative 0.36. If you remember that we discussed that this particular problem, its minimum will be at negative 2. So you can see that in one iteration we have jumped from 7 to negative 0.36. So we came pretty close to the actual solution in first iteration itself. We have to continue this process until the solution converges, and the solution will converge when this decay will be very small, less than the tolerance that we will set. Decay is actually the negative of gradient. Decay being 0 means the gradient is 0, and that will be the point of minimum of this function. So when decay is sufficiently small, then we can assume that, oh, all right, it is close to 0, and we can terminate our program there. Now to summarize, we have discussed theory and one example of steepest descent method. For your exercise, the way we have calculated x1 from x0, here you go from x1 to x2 next iteration and see that if it is indeed converging. So that's all for this lecture. Thank you, and I'll see you in next class.